All right, cool. So you guys are all in trouble, so we have to move classrooms. Sorry to let you know. We started looking at exams 3, and so we have to go to remedial organic chemistry. No, I'm just kidding. I'm joking. No, they're having meetings with the board of trustees, and apparently they like the other classroom better. So, right side of the hallway is the cool side. So here we are. Okay. Anyway, we'll be back over there on Monday and everything. So it should all be for today. But anyway, so we're making our way through the Alkyne chapter, and we're pretty much done with it. Okay. Remember, the theme of the alkynes is that they're exactly the same as alkenes, but twice, right? So it's like one of those fancy infomercials, right? But wait, there's more, right? So you do one reaction, you do the other reaction right after it, okay? But they have a very special purpose, and they have a very unique functional groups that we can make at the end of them, right? Remember, what we talked about last time is that when you're doing hydrations of your alkynes, we end up with ketones and aldehydes. Okay? And we really don't have any other methods of making ketones and aldehydes yet. Right? Thank you. Right?
Yeah.
Yes. Okay, so, and on the next exam, right, you guys say, oh, we got to make a ketone and an aldehyde. Your thought should be, hey, I know that the functional group I have to make before this has to be an alkyne. And then your thought is, hey, the only way we know how to make an alkyne is from vicinal or geminal dihalides. Got it? So we have a sequence of steps that get us to making a ketone or an aldehyde. We know we have to have an alkyne, and we can only make alkynes from certain vicinal or geminal dihalides. Right? That's all it comes down to. Everyone follow along with that? What we're saying? Okay. So now, hang on to that thought, and we will. Well, I'll ask you guys that exact same thought again in maybe about 20-ish or so minutes, if not a little bit less. Okay. So, tautomerization is the process that we went through, right? How we can convert an alkene-ol, an ene-ol is what we call it, an enol to the ketones or the aldehydes. Enols are transient species. We will never really be able to isolate and keep one separate, is what it is. Okay? So enols are not something that we can trap and put into a bottle under normal conditions. So when you guys are going through and you're doing a synthesis, if you end up putting an alcohol on an alkene, you guys can't really stop it from doing that tautomerization. The second semester of OChem, we're going to come back and we're going to use those enols to do some other chemistry with. Okay? This is an equilibrium, right? That's why I have those two-headed arrows in there. This is an equilibrium. The double bond O is by far favored. Okay? And that's something important to kind of keep in mind. Carbon double bonding to oxygen, that's a good thing. Carbon loves its friend oxygen, and oxygen loves its friend carbon. And so there's a strong thermodynamic drive to make ketones or aldehydes. Okay? So the question might be, well, why does this happen? Carbon-oxygen pi bond is stronger than the carbon-carbon pi bond, right? That's the reason. Okay. Good? You guys want to think a little bit? I don't care what you're saying, Darian. Too bad. Gotta think anyway. I like to just ask you guys questions and then do whatever I wanted to begin with. Yeah, it's good to be the king, as they say, right? Okay, go for it. Oh, I did forget about cold. I haven't done that.
What room is this?
This is 1029.
I think Jose was that way.
Good thing it was late, right? I could yell at him the whole way. You texting me over here?
Yeah, I texted
Okay, yeah, just tell him over here. So when he comes in, make sure everyone just stares at him. I think he'll appreciate it.
He probably walked in on that meeting.
What happened to you? What's wrong with you guys? Yeah, I only emailed my favorite student. I'm just kidding. I'm sorry. That's completely my fault, guys. I forgot about it, and I remembered when I was walking down the hall and I saw people with expensive suits. I'm like, uh-oh. So, sorry about that, gentlemen. What class did you guys walk into, though?
I wasn't there.
It was
I
empty.
saw the body and I was like, what?
It was
I went
empty,
to-
and then Dr.
I went to
Quintero
a-
and his
yeah.
class came in.
Oh, I got a guest lecturer. So for you guys walked in, so I'm asking them about how we can do this transformation there is what it is, right?
So are we moving here until the end of the?
No, back on Monday we'll be back over there, yeah, it's just for today. They just wanted to make you guys really cold for a day. You were not here. Oh, jeez. You have your book with me? You have your book with me? You have your Taylor with me? She's got a book. That's the question. How do you avoid that from happening? This is the question. So what's the problem here? So the problem is, can we go directly in one step? If we try to hydrate an alkyne, right? If we try to hydrate an alkyne, it's going to end up as some kind of carbonyl, okay? Do you guys see what I mean by that? We can't directly hydrate an alkyne and expect it to end up at the alcohol yet, okay? We'll learn a couple of reactions next semester on how to do that though, okay? Okay, so we can't hydrate an alkyne. What can we hydrate? An alkene. Okay, so if the alkyne is causing us problems, what should we do? Get rid of it, right? Okay, so how can we get rid of an alkyne?
The strong acid.
Okay, what would that do?
Wouldn't it turn into an alkene?
It would continue to react, right? Remember, we can't really stop it from reacting more than once, right?
Okay.
Strong base, what's a strong base gonna do? Okay, where's our leaving group? What else can we do? I saw you guys, some of you guys had excellent answers. Who was it? Kate or Catherine? One of you guys. Go for it. I think it was Kate. What did you have?
Sodium over NH3.
What? Sodium over ammonia? What kind of radical reactions are we doing there? What does that do? What does sodium over ammonia do to an alkyne?
What was the trans configuration? It's reducing it.
It takes an alkyne into what functional group?
Well, it turns the alkyne into an alkane.
There it is. Got it? So if the alkyne's causing us problems, get rid of it. I don't need this crap. All this negativity in my life. Or electronegativity, I mean. I'm sorry. I only got like 4 more lectures to get all my stupid jokes in with you guys, so I gotta cram it in before the break. Alright. Okay, so if I ammonia, right? Sodium and ammonia will get an alkyne into an alkene. Okay. How does an alkene react? Are you guys more comfortable with working with those? Okay. Can we hydrate an alkene? Okay. Is it going to overhydrate? Is it going to tautomerize? Is it going to do any of that stuff? No. Okay. So sulfuric acid and water, just fine. You could use your oxymercuration. You could use your hydromeration, whatever you want. Got it? So if the alkyne is going to cause problems by reacting twice, turn it into an alkene and just work from there. Got it? Now next semester we'll learn how we can take a ketone into an alcohol, right? We'll learn about how to reduce these kind of things. And then we can go about this in a different method. But as a single step, we can't do this though. We can't go directly from an alkyne into an alcohol. We'll need at least 2 steps to do it. Okay? All right. So we have a situation when we have a terminal alkyne. Okay? And that terminal alkyne is going to, well, actually, hang on. So, shoot, yeah, well, I'm already into it. Never mind. Okay. I went off of the track in my head, which is very shocking. Right. But anyway, so when you have a terminal alkyne, right, we have the alkyne that's at the end of the chain there, right? Okay, fair enough. If I put that terminal alkyne in the presence of this, what's going to happen? Yep.
It's gonna
Deprotonate? What? I don't believe you. How in the world could that happen? What are you seeing?
Because the NH2 grabs the hydrogen that's in up end of it,
How do you know?
because it's negative and wants the proton.
Okay, fair point, right? Sodium, NaNH2. What do we know about NaNH2? It's a what?
strong
A
base.
what base? Extremely strong base, right? Extremely strong base. That's why we can use it to make our alkynes to begin with, right? So it's an extremely strong base. So here, just for argument's sake, right, are the products for this reaction, okay? Powerful base, a maybe acidic hydrogen, right? Then we have this plus ammonia gets made. How do we know when an acid-base reaction is going to happen? How do acid-base reactions work? What do we have to pay attention to? That's always important. It's always important to look for charges.
Whether something can act like a loose base or loose acid.
Right, we have to know whether something has a proclivity to act like an acid or base. That's always important. What numerical values help us determine acidity? pKa's. What's the pKa of an alkyne? The terminal alkyne. Way back, chapter 4. Almost 300 pages ago in your notes. We were talking about what factors impact acidity. And we talked about alkanes versus alkenes versus alkynes. We talked about hybridization, right? Anybody find it, or do you want me to just spare you guys the misery? No, keep searching. Good to be the king. Huh? 25. I used to bring Jolly Ranchers, like when, no. I don't know, I'm so mean now. Don't give stickers, no more Jolly Ranchers. No. So, I'll have to do that for next semester, I guess. But anyway, yeah, 25, a pK of 25. Do you, are you still on the page? What's the pK of an alkane?
50.
About 50, right? 25 orders of magnitude more acidic than an alkane. That's a massive change. Now, granted, does that mean that it's a good acid? No, they suck, right? 20 pK of 25 is pretty lousy. But for a hydrogen bound to a carbon, that's really darn acidic, right? So here we have a pKa of 25, right? Here our pKa is about 35. Okay? How do we know which side of an acid-base equilibrium is favored?
The more basic The weaker.
The weaker what?
Weaker acid.
Exactly. The weaker side is favored. Why? Why would the weaker side be favored? Well, if you're not the weak side, what are you? The strong side. How do strong acids and bases want to react? Like acids and bases. You guys get what I'm saying with this? If you're a strong acid, you're going to act like a strong acid, so the reaction's going to happen. You guys following along with this? So it's just, no. So what does the pKa mean here? Which side's the weaker acid? The one with NH3, right? The 35. You guys with me on this? So is this an acid-base reaction that will happen? Absolutely. But you need a fairly strong base to do this. So sodium amide will deprotonate that terminal alkyne. Okay? Now, the pKa of that alkyne was 25. And you guys told me that that is a particularly weak base, right? And weak bases make, weak acids make strong bases. So is the deprotonated alkyne, right, is this here a strong base? Yes, it is. Do you guys get what I'm saying with this? So how will that alkyne behave? Like a strong base would, right? You guys with me? You sure? 100%? So what if I do this reaction? Well, what if I write it properly? What happens after step one? Step one, we deprotonate our terminal alkyne, right? Then what do we do? What do we have in part two there? Nothing. I think you guys got it wrong. What do we have in part two?
We have a weak base.
What's this? Is that last
Oh,
one? An alkane, okay. What else? Good leaving group, what else? Nucleus on where?
Oh, wait, no, do that.
Strong base, right? We've got the deprotonated alkyne there. What flavor leaving group? Interesting. So we got a strong base, which also happens to be a yeah. A relatively unhindered nucleophile, huh? Got a linear geometry, hard to get less hindered than that. So we got a powerful base, a good nucleophile, well, an okay-ish nucleophile, I should say. A primary leaving group. So what's going to happen in the second step there? SN2, right? For primary leaving groups, even if you have a strong base, SN2 is favored, okay? So what's our product going to look like in the second step here? So our second step, right, we're going to add this to that. So there's our alkyne. Okay? 1, 2, 3 carbons here, 1, 2, 3 carbons there, right? 1, 2, 3, 4, 1, 2, 3, 4. Okay? Guys got it? So, before I get to my, I guess, main point with this, go through and draw me the mechanism for these two, okay? Both these steps. Yeah. Good. Looks good. I thought you dropped the card, I'll just double check. No, I'm just kidding, sorry.
I just checked back.
You're all good. Careful, that's going to hit carbon, that's attached to the lead group. When you're doing an SO2, you hit the carbon back to the lead group. All right, looks like you guys got it. What's so useful about this? Aside from me being able to take off points later on. What practical utility does this have? So remember what I'm asking you guys to look at, okay? It's just like when I started out the lecture today was, I said, hey, how many other reactions have we found that make ketones and aldehydes? And the answer is, not too many, right? What did we do in this reaction that we have, I'm double checking, we have not done anywhere else in any of our reactions yet?
Maybe turn it off Alkyne in the middle.
So what bond did we end up making at the end of this? A bond between what? A carbon and a? How many other carbon-carbon formation bonds have we learned? That's right. None, right? So this is the first one that we've learned. You think that's pretty important? Okay. So now we can start to string together larger carbon chains. Assuming that we set this up properly, right? And what I mean is we have to have a terminal alkyne and we have to have a primary leaving group. Got it? So we have to have pretty specific conditions, but we can now string together some larger carbon-carbon chains. Good? Now, truth be told, these are still relatively lousy reactions to put together two carbons, but for what we have at the moment, that's what we can use. And next semester, we'll teach better ways of doing it, okay? But at the moment, good stuff, okay? So what have we learned so far in the last, oh geez, I've already been talking for like 30 minutes. Boy, oh boy. Time flies when you're Alkyne. And I'm what?
When you're struggling.
I'm struggling. Oh, you got, oh, that's okay. No. But right, so we've learned that alkynes are useful to make two very specific types of functional groups, right? Our ketones and aldehydes, and now we can link together carbon-carbon double bonds. Excuse me, link together carbon-carbon bonds. Okay, very useful. I'm being subtle with my hints in case you guys can't tell, right? I'm giving you small little clues for what we might expect to see later. Right? Okay. I'm not very good at subtlety, by the way, so there you go. All right? Cool. And then, oh, right, I forgot the thing that I wanted to start out with. The top one there, right? BR2, keep it cold and dark. What reaction are we doing?
Addition.
It's an addition, specifically our halogenation, right? Adding BR2 or Cl2 or in some cases I2, right? What mechanism does it go through? Sumo, our three-membered ring, right, with the positive charge, right? Can you guys draw that mechanism? Well, should you guys be able to draw that? Yes, I know you guys can, right? And we know that it makes a racemic mixture and all the blah, 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 right? So, how's that reaction going to work when we have an alkyne? The exact same way, but twice. Got it? Does the mechanism change? Nope. Will it still make a racemic mixture? No. Why won't it make a racemic mixture? Well, my product's going to look like this, right? Why won't it be a racemic mixture?
Because you have the wood and the dash on both, not just the same exact.
They're not chiral centers, right? You guys get what I'm saying? Like those aren't chiral centers anymore, so it doesn't matter about the wedge and dash. Good? Okay. There we go. Alkyne's done. Now we know everything about alkynes. But wait, there's more. All right, so we're going to take we'll end up this semester here with a new mechanism to know, okay? And a new set of reactions. And just because we do it last doesn't mean that it's less important or something. It's just, there's two options. I could have either done this as the first chapter when we learn mechanisms, or you do it at the end. Because these mechanisms are going to behave differently from all the other mechanisms that we learn. And what I mean by that is every reaction that you guys have done so far has involved the movement of pairs of electrons. Okay, lone pairs make bonds. Bonds break to make lone pairs. Okay, so we're always dealing with just pairs of electrons is what it comes down to. What we're going to do now is we're going to do what happens when you move one electron at a time. Okay, so what happens when we have radical reactions? Right, so when we're dealing with a single electron, we call that a radical reaction, is what it is. Okay? And this is, what is it, chapter 10? Where is it for you guys?
Chapter 10.
Yeah, chapter 10, okay? I was getting there. So chapter 10 is where we'll end up the semester though, okay? Don't worry, it's just what? 12 chapters of organic chemistry to know? It's the only class you guys are taking, so not a big deal, okay? Okay, so chapter 10 then is where we're launching into here. All right, ready? I'm going to ask you guys a question. What reactions can you guys do?
SN1, SN2, E1, E2.
Everything. Well, which ones can you do? Maybe everything, right? Some of them are going to be faster, right? Some are going to be a little bit slower. We could eliminate, we could substitute, right? So like Freddie said, we could do everything if we set it up under the right conditions. Got it? Okay, what reactions can you guys do?
Addition.
Addition? Well, it's already a saturated alkane, right? Can't add anything. Well, there's nothing to eliminate, right? There's no leaving groups. Well, that's not true. Huh? That might be true. Why would you say that? Come on, you guys know exactly what reaction you can do here. It's the reaction that you guys all desperately want to do every day that you guys come to lab. Huh? That's what you want to do? I could, all right, for you, I'll make that happen, Jose, right? The one reaction that you guys always find infinitely amazing. Kaboom.
Magic.
Combustion, right? Could you guys burn that? Sure, that's butane, right? Butane's a good fuel, you can burn that. But that's about it, right? What are the reactions? We can't eliminate, we can't substitute. Okay? So we're stuck. Why? What are we missing there? What's one of our fundamental questions of assessment?
Leaving group.
Do we have a functional group that could act as a leaving group? Is it weak? Is it pure, strong? Is it primary, secondary? Right? We don't have anything on there. Okay? So one of the important parts to come out of chapter 10 here, the radical, is we can actually add functional groups. Now we're going to add very strange functional groups that you guys have never seen before. They're going to be called halogens. Okay? I know. I was amazed also. Okay? But do you guys get the point? So the important point here is we can start with an alkane, we can add a halogen, and do you guys know a lot of reactions with halogens? You bet. Okay? So these typically, what I mean, are some of the most important reactions. Because, we can go and we can find methane, right? Trapped underground where we get oil, and we have all these alkanes, butane we can find, right? But they don't have any functional groups on us to do something to turn them into useful materials, okay? We can burn them for fuel, and that's certainly important, right? But if we want to turn these into, value-added products, as they call it, right? Things that we can do chemistry with, we have to start by adding certain functional groups to it. And this is one of the fundamental things that we can do, okay? So here's the reaction. We're going to add Br2, okay? And I'm going to heat it up and put it under light. Got it? Now I've got a question for you. What's the opposite of hot? What's the opposite of light? Do you guys get what I'm saying with this? Remember I said that when you do halogenation, it's important that you keep it cold and dark. Because if you do the opposite, it's going to do a different reaction. So as soon as you put bromine under and start to heat it up, or start to shine certain wavelengths of light on it, they're going to start to break apart and form radicals, is what it is. Okay? Now, this is sometimes abbreviated as delta, right? Not to be confused with the cyclopropane, but the delta symbol, right? Or H nu, right? Where energy, right? E equals H nu, right? If you guys remember from Gen Chem. Of course we do, Dr. H. Okay? Right? So you're just adding energy into this system. That's all that's saying. Remember, heat and light are just energy. Okay? And so cold and dark is just don't give it energy. That's all we're saying with that. Okay? So if I have two things that are bound together, okay, what we've been doing so far when we show a bond breaking, right? We've been drawing an arrow like this, right? And that represents both of those electrons are moving to whatever species in whatever that X represents, right? A heterolytic cleavage of a bond, right? Heterolytic just means unequal breaking, right? So heterolytic cleavage is what you guys have been doing all semester long. When we're dealing with radicals, there's a couple things that we have to take into account. So first thing is we're going to equally split that bond, which means each of those atoms, whatever the X's might be, right, are going to get one of the electrons from that bond. So that's a homolytic cleavage, okay? Now to represent the movement of an electron, okay, I don't know why it didn't change here. Let's try this one more time. You draw a single-headed arrow, okay? Double-headed arrow, move two electrons. Single-headed arrow, one electron.
So then when you draw two, one going to each.
Exactly, right? So I am moving one electron here, okay? And so then my other electron goes there, okay? Now notice, there's a couple of important things here, okay? So my products here will look like this, right? We'll have that, and we will have that, okay? So we split here for each of those to get an electron. Got it? So that's how we break bonds with radicals. Guess what I'm going to show you next? There you go. But you guys can probably figure it out, right? Because how many electrons does it take to make a bond? 2. I've got one here and one here, and I've got to move those two together. Got it? So the arrows to do that, we're going to point from the electron to in between the two atoms. Okay? Doing it all wrong. You guys with me on this? So why is this unusual? Well, remember, now that we're only moving single electrons, we have some different rules. Okay? And what I mean is this. So just for argument's sake, right? Are you guys ever going to see double-headed arrows that point at each other? No, you will not. Are you ever going to see double-headed arrows that point away from each other? Right? Will we ever have double-headed arrows that look like this? No, we will not. Okay? Do you guys catch what I'm saying? There's different rules when removing a single electron. Okay? Don't get the patterns of radicals confused with the patterns of pairs of electrons. That's one of the tricky things, okay? Now, we will be spending basically this chapter on radicals. And then there'll be something that we use, but there really aren't any other mechanisms that we'll learn with them. Right, so we have this kind of like one, how do I want to put it? Not random, what's the word I'm looking for here? Oddball chapter that we deal with these mechanisms, right? All the rest of the time we'll be dealing with pairs of electrons again, right? So just be aware of that, I guess is all I'm really trying to say. Okay? So, to do a radical mechanism, which I do expect you guys to know, there's 3 steps. Okay? There's an initiation step. And the initiation step is where we form a radical to begin with. So for our halogenation reaction, our radical halogenation, we start out with our bromine, we zap it with some energy, okay? And we break our bond apart. And we end up generating 2 radical halogens, okay? Now this step is reversible, right? You can imagine that these 2 radicals could come together and reform that bond, right? But remember, when we're dealing with a mechanism, we're just saying what are the logical steps to get to the product, right? We know that there's a theory of microscopic reversibility, right? These things can go back to where they started. Okay, there's step 1, form something. Step 2 is propagation. Okay? Propagation is where you start with a radical and you make another radical. So, here, okay, yep.
What would be the charge on the bromine? Would it be 1?
Good question. Yeah, I shouldn't have skipped that. So let me fill in the rest of the lone pairs and then ask your question again.
What's the charge?
What is the charge, Amy? Got her. It's a good question, right? It's a very good question. What's the charge in the bromine? It's neutral. Pretty unusual, huh? Pretty unusual. So, neutral charge in our bromine. So, that does kind of lead to the thought of, remember, one of the important things I always ask you guys to do is find your positives and your negatives, right? And I said that will get you through organic chemistry. I didn't say it's going to answer every question because it's not how it works here, right? But 99% of the time, we're just looking for negatives and positives. But radicals behave differently from all that, right? So very, very good question. Thank you, Amy. Right? Propagation. We start with a radical, we make another one, okay? Now here's what we're going to do. We got to make a radical with this carbon here, right? Okay, so watch what happens. Ooh. All right then. I don't know what my computer's been acting up all semester, but that's okay. So watch. This. What does that set of arrows represent? Bromine sends its radical, right? The carbon hydrogen here, 1 electron comes together, so we're making a bond between the bromine and the hydrogen. Got it? But as with other rules, if we make a bond, we have to break a bond, okay? And so we are going to break that there, right? So we have 3 electrons moving, okay? We have 3 electrons moving, so we have to have 3 single-headed arrows to represent that. The black and the pink here break the CH bond, right? And the blue and the pink make the bond between the hydrogen and the bromine. So what's our products here? Our products here are Br, just for argument's sake, we'll use that color, pink H, right? And here we have a carbon radical, okay? Good. So we start out with a radical and we end with a radical. That's what a propagation step is, right? Remember, to propagate just means to continue, right? To make more. I propagate headaches for my students, right? And ulcers occasionally, all right? Okay? So, initiation, propagation, and then the last one is termination, okay? Termination is exactly what it sounds like. We start with a radical and we consume it, right? We don't have a radical at the end. So 2 radicals coming together. So here's one of our radicals. Okay? And here's our other radical. The other bromine that we made at the beginning. Got it? Remember, we made 2 bromine radicals in the first step. Okay? So we bring these together. We'll do that. We'll do that. Cool. Ta-da! What did we do? We started out with an alkane that had nothing on it, and we end up putting a halogen. Can you guys do some reactions with halogens? Sure, right? Now the world is your toy box, right? We can start with a plain old empty carbon whatever, right? Some kind of carbon compound, and you guys can add a halogen, and you can eliminate, or you could substitute. We could turn it into an alcohol, we could turn it into ketones, we can turn it into anything that you guys want, right? But we have to have a functional group there to begin with, and this is our way of adding that. Got it? So you guys feeling pretty comfortable about this? Okay.
Dr. H,
Yeah.
how do you know which carbon is gonna?
Right, that's the question. So, my question was, you guys feeling pretty comfortable with this, right? Wait a minute. This is far too easy to write a whole chapter about. Alright? They're starting to get suspicious. Okay, so here's the good news. This is how it works. Alright, so a radical mechanism always has these 3 steps. But the question that Annie asked is, again, the question. Say, how do we know that that's the hydrogen that gets abstracted, right? Why did I pick that one? Well, it's nice, it's in the middle, it was green, no pink, sorry, okay? That's the question. And we're gonna have to learn about what happens at that propagation step, because that's gonna cause problems, okay? So we're gonna have to come back and put some polish on this, but this is the mechanism. If I ask you guys, show me the mechanism for a radical halogenation, this is what it is, okay? In reality, it gets kind of messy, but we have to come back and introduce a couple of ideas there first, okay? Sound good? Cool. So I think that's a good place to stop for today, because the next part that we get into is going to take a little bit of time to develop, right? So, and I gotta stretch out the course, as much as I can. I gotta just add content. Oh man, more reactions. So, I'll see you guys on Monday, and I should have your exams and stuff back by then. Okay.